Slideshow is intended to be seen before we do Excel Lab 3 in class for Business Analytics 1. It does do an overview of the types of topics that are going to be involved with that Excel project. So there are going to be three main tasks. First, we're going to make and use a contingency table. Secondly, we're going to calculate expected values. And third, we're going to update prior beliefs using Bayes' theorem. Now, one of these topics can be a bit confusing. The other two are really new topics that aren't covered very well, if at all, in the textbook. I did mention them in the previous video we used for preparation purposes. Here I'm going to go into a little bit more detail on these to kind of flesh them out so that we are very well prepared when we get into class to do the lab. So first, the contingency table. So remember, the basic concept of a contingency table is that each cell shows us the frequency or the relative frequency of some combination of outcomes. Right? So normally we're going to have two traits, and so within each cell in this table it tells you how many observations have that combination of traits. In terms of what we use it for, we use it to calculate conditional probabilities very easily. So when we make one, what we end up doing is reverse engineering. We start with the conditional probabilities that we know. We then can reverse engineer and get that contingency table, which allows us to calculate any conditional probabilities we don't know. Here's just kind of a basic use for it. So we have two plants, plant A and plant B, and they produce units of a good. Some of these units end up being defective, some are not defective. And we might be interested in things like, well, what is our overall defect rate? Or what is the defect rate for each plant? This table will allow us to calculate that. So I'm going to answer 5 questions here. First, what is our overall defect rate? So to do this, we would find the total number of defective units, that's 766, and divide that by the total number of units, 100,164. So that gives us an overall defect rate of 0.0076, that's basically 0.76%. Then we might be interested in what the defect rate is specifically for plant A. Well, in that case, we narrow down, we only look at those units that are produced in plant A. So of those, 527 are defective out of the 68,963. So do the division, and we find out that, again, 0.0076, or about 0.76% of the units produced in that plant are defective. We might want to do the same for plant B. So with plant B, we would narrow down, only look at those units produced in plant B. So we look in the plant B row. There, 239 of them were defective out of 31,201, which gives us an overall plant B defect rate of 0.0077, so slightly higher than the average. Now this gives us a very different picture than if we were looking at the probability of a defective unit being from plant A. So that would be the next question. What is the probability a unit is from plant A given that it's defective? In this case, we'd only look at that left column, the defective units, to figure out this proportion. So plant A, given it's defective, that'd be 527 units out of the 766 that are defective. That's basically 68.8%. The probability of being from plant B, given that it's defective, is roughly 31.2%, doing the same kind of calculation. 239 defective units from plant B divided by the 766 defective units total. Now notice here we get a very different picture. So the question of which plant has the higher defect rate is very clearly plant B. Not by much, but it's very clearly plant B. On the other hand, if we're asking the question of where do most of the defective units come from, that would be plant A. So I think we can see that there would be a practical application to this question. Now that we've seen how we can use a contingency table, let's show how we can create a contingency table based on a few conditional probabilities. So in this case, we're not going to create the whole thing. We have a very specific question we're trying to answer. But what we know are a few conditional probabilities. First is the overall defect rate for our plants is 1%. Secondly, we know that plant A produces 60% of our product. And third, we know that half of the defective units we found come from plant A. We want to figure out what plant B's defect rate is. Now, it's not immediately obvious that we should be able to do that, given that most of the information we have in any kind of detail is about plant A. But it turns out we do have enough to answer that question. So let's go ahead and show how we can do that. So we're going to go step by step through each of the things that we know and use that to fill in various elements of our contingency table. I started by just assuming that we're looking at a hypothetical 1,000 units, so I have 1,000 in here in the grand total that we find in the bottom right of the contingency table. So first, the overall defect rate is 1%. So let's go ahead and fill that in. We know that 1% of 1,000 is 10. So of these 1,000 units, 10 total should be defective. So we'll fill that in at the bottom of the defective units column. So there's our total. The second thing we know is that plant A produces 60% of the product. We know there are 1,000 units being produced. 60% of that is 600. So we can put that in for plant A's total production. So the plant A row, the total will be 600. We also know that half of the defective units come from plant A. So if there are 10 defective units, half of that would be 5. So it tells us that 5 defective units came from plant A. Now we're trying to figure out what plant B's defect rate is. At the moment, I don't have any information about plant B, but it turns out we can fill it in using some just basic logic. So first, the total produced. We know that overall there are 1,000 units produced. We also know that plant A is producing 600 of them. So then follows, since every unit is produced either by plant A or plant B, that 400 must be the number produced by plant B, because 600 and 400 together would add up to the 1,000. The next thing we know is that if there are 10 defective units, and 5 of them come from plant A, the other 5 naturally must come from plant B, since every unit comes from one of those two places. Now we're in a pretty good place, because now we can actually calculate plant B's defect rate. We know how many defective units they've produced, 5. We know how much total they've produced, 400. So we do the arithmetic, and we find out that plant B's defect rate is 5 divided by 400, or 1.25%, a little bit higher than the overall defect rate. And is expected value. So the basic concept of expected value is basically the mean, except that we use the term mean when we're referring typically to a set of data that we've gathered, but expected value is applied to a probability distribution instead of a population or a sample. And so the formula for that, for expected value, is you take all of the different possible observations, what I'm going to call x here, take the probability of that observation, multiply it by the value of that observation. Do that for every possible observation and then add everything up. Let's look at an example. So here's a very simple example. So we know what is the expected value of rolling a 6-sided die. So a 6-sided die typically has 6 sides that are numbered from 1 to 6. So 1, 2, 3, 4, 5, 6. So what I would need to do to calculate the expected value is take the probability of rolling each side, multiply by the value of that side, and then add it all up. So that'd be 1/6 is the odds of rolling a 1. So 1/6 times 1, plus 1/6 times 2, plus 1/6 times 3, plus 1/6 times 4, plus 1/6 times 5, plus 1/6 times 6. So we do all of that arithmetic, we find out, we come up with 21/6, which simplifies to 3.5. Right? So what that means is that you can expect, right, from rolling a die, if you roll it a whole bunch of times and take the average of all of those rolls, you're going to end up with something very close to 3.5. Now we can also apply this to cases where not all the results are equally likely. In this case, the probability was always 1/6. You can easily change that. So let's look at another example that's a little bit more business-y. So here's a business application. So we have a particular investment that performs differently depending on the state of the economy. And this is typical of most investments. So in this particular case, if the economy does really, really well, I'm going to say it does great, then this investment will return 20%. A good economy will get 10%. A fairly flat economy, we can still get 5%. Or if the economy is in a recession, then we'll lose 20%. Then each of these states of the economy also has a probability attached to it. So 0.1 for a great economy, 0.4 for a good economy, it's typical, 0.3 for a flat economy, and 0.2 for a recession. So to find the expected rate of return on this investment, that's just the expected value, we take each probability and multiply by the investment return. So 0.1 times 20%, 0.4 times 10%, 0.3 times 5%, 0.2 times negative 20%. Do all of those multiplications, add up and get the total, and we get 3.5%. Let's turn to Bayes' theorem and how we can use it to update our beliefs. Now, what Bayes' theorem does, as a reminder, is that it allows us to reverse the order of conditionality for a probability. So the probability of A given B, if we apply Bayes' theorem, we can calculate the probability of B given A. The formula for it is the probability of B given A is equal to the probability of A given B times the probability of B divided by the overall probability of A. Now I have here on the slide how you can derive this. Don't worry too much about that. We'll just be using the formula. So it turns out we can apply this, right, to the idea of updating our beliefs. So there's a group of statisticians that would call themselves Bayesians that believe that we should really think most of the time in terms of Bayes' rule. And they specifically think this in regards to our updating about beliefs regarding what theories we accept as being true. So what Bayesians suggest is that we have a number of different theories that we use to make our predictions about reality. And what our predictions really are is we think about all these different theories, the outcomes that each of them would predict, and then we weight those, and then effectively calculate the expected value to figure out what our result would be expected to be. Then, though, what happens over time is that these theories that we hold are tested by the data. So as we observe things, we adjust our beliefs regarding these theories. So our beliefs about the likely truth of each theory is going to be adjusted based on our observations and how well predicted whatever the observation is by each theory. So those theories that predict well are going to end up gaining more weight over time as we observe things. Those that predict poorly are going to lose weight over time, or perhaps be discarded entirely if the theory is totally inconsistent with the data that we observe. So here's a simple example of this. Suppose that I have a coin. It might possibly be fair, that has 50% chance of heads and tails. It might be two-headed, or it might be two-tailed. You have no idea which. I have this coin, I'm refusing to let you examine it. Right? So what do? You form these prior beliefs based on your instinct, impressions, prejudices, whatever. You have some guess as to the likelihood that this is a fair coin versus two-headed versus two-tailed. Let's just, for the sake of the example, say that you start out by thinking, well, Professor, I think that you're a fair person, so you probably have a fair coin. So I think that's an 80% chance that it's a fair coin. If it's two-headed or two-tailed, I really don't have any way to figure out which one of those it is without actually examining the coin. So I'll just say if the other 20% that it's not a fair coin, I'll split it evenly. So 10% chance it's two-headed, 10% chance it's two-tailed. Right, so here's the description of the theory. So the fair coin, you gave it an 80% probability based on your prior, that is, before you gathered any data about this coin. Right. Then, according to that theory, the probability of a heads, if that theory is true, is 50%. The probability of a tails is also 50%, according to the fair head theory. Another theory is that it's two-headed. Now you gave this a prior probability of 10%. You think there's a 10% chance that this is what is the case. Well, if it's a two-headed coin, then the probability of a heads, according to that theory, is 100%. But if you flip the coin, it's going to land on one head or the other head, right? Which means the probability of tails is 0, according to that theory. On the other hand, there is the last theory, which is that it's a two-tailed coin. Again, we assigned a 0.1 probability or 10% probability to that being true. And if it is true that it's a two-tailed coin, then the probability of heads is 0. You can't possibly flip a head on a two-tailed coin, which means it's a 100% chance you're going to get tails on that coin. So I want to know, what is the probability of flipping a head given that we don't actually know which of these coins is the one that I'm holding in my hand? So to get that, we calculate something very similar to the expected value. So what we'll sum up each probability of heads given the theory, multiply by the probability of that theory, based on whatever your prior was. So in our case, that'd be what's the probability of a head given that it's a fair coin, that's 50%, multiply that by the probability of it being a fair coin, that's 80%, 0.8. Add to that the probability of it flipping a head if it's a two-headed coin, times the probability of it being a two-headed coin, so that'd be 1 times 0.1. Then finally the probability of it being a head, given that it's a two-headed coin, multiplied by the probability of it being a two-headed coin, so that'd be 0 times 0.1. Add this all up, and we end up with 0.5, which tells us that there's a 50% chance of heads based on your priors. Now what happens? We flip the coin, you look at the result, it turns up heads. So I want to know then, what is the probability of getting a second heads? All we need to do to calculate is to update our beliefs based on what we've just observed. So we now have the fact that we did on that first flip, we got a heads. That tells us something, so let's take that into account. And this is where Excel is going to become very, very useful in allowing us to use Bayes' theorem, which tells us, in general, the probability of B given A equals the probability of A given B times the probability of B divided by the probability of A. What we can do here is change all the B's to theory, change all the A's to data, and this is the form that you'll often see Bayesians advocating that we should use when we update our beliefs about different theories. So the probability of the theory, given the data we've observed, should be equal to the probability of the data given that theory times the probability of that theory that we had before, that's the prior probability, and divide that by the probability of observing this data according to all the theories combined. In our case, we have those three theories. The data is that we just observed heads being flipped. So let's walk through how we do this. Right, so the first theory was that it's a fair coin. We gave it a probability of 0.8 to start with, and we have the probability of heads being 0.5. So we multiply those two together, that gives us 0.4. Now for two heads, we have prior probability of 0.1. A probability of a heads, if it is in fact a two-headed coin, it would be 100%. So multiply those two together, that gives us 0.1. The two-tailed coin, we gave a prior probability of 0.1. The probability of getting a heads in that theory is 0. So multiply those two together, and we end up with 0. Now to adjust all of this, we need to take and find the probability of the theory given that we just saw a heads being flipped. So we've already done the calculation for the numerator in Bayes' theorem, that is the probability of heads given the theory times the probability of the theory. Now I just have to divide by the overall probability of heads, which we calculated as being 0.5, just taking the 0.4 and the 0.1 and adding them together. So doing that, we end up with now, having updated our beliefs, the probability of it being a fair coin stays the same. It's still 0.8. The probability of it being a two-headed coin now jumps from, originally it was 10%, now it's 20%. And the probability of it being a two-tailed coin falls from 10% to 0, because we know you can't possibly flip heads on a two-tailed coin. Right? So we've just ruled out the possibility of it being a two-tailed coin. The probability of it being a fair coin stayed the same. The probability of it being a two-headed coin just jumped. It, in fact, doubled. Now, based on this, right, what is the new probability of having a heads? So if I flip the coin again, I'm going to end up with a different probability of a heads happening. Let's walk through that. Right, so thinking about this other heads being flipped, what is the odds of it happening? So we do like we did before. 80% chance is a fair coin. If it is a fair coin, then 50% chance of heads. That gives us 0.4. 20% chance that it's a two-headed coin. If it's a two-headed coin, we're definitely getting heads. So we multiply that by 1 and gives us the 0.2. So add it all up. Now there's a 60% chance of us flipping a head based on our beliefs about these two theories and the likelihood of each being true. What if we flip heads again? So we find out not only did we get the heads the first time, which we thought was a 50% chance, but now we get it a second time, which we thought was a 60% chance. What does that do to the probabilities for each theory? Well, we can fill in that last column. After all, we already have the numerator of the Bayes theorem. That's what is in this column with a 0.4, 0.2. So we just have to divide by the total probability of that second heads happening, at 0.6. So the probability of it being a fair coin is 0.4 divided by 0.6. That gives us 2/3, or basically 67%. So we saw now a drop in the probability that it's a fair coin. Meanwhile, the probability that it's a two-headed coin is going to be 0.2 divided by 0.6, or 0.33. So again, the probability increased from 20% now to 33%. So as we just keep flipping and see more and more heads, that is going to increase the probability that we think it's a two-headed coin. And in this case, that has to eat into the probability that it's a fair coin. Now we could keep doing this and see, well, suppose we get heads again and again and again. Right? What does that do? And we will see that general trend as we come to believe more and more that it's a two-headed coin. On the other hand, if we flip and we find a tail, we're immediately going to rule out the possibility that it's a two-headed coin because we know that's not possible. And again, right, very much like it did with the two-tailed case before, we can use Bayes' theorem with this kind of setup to update our beliefs to show that, oh, we no longer believe that it's a two-headed coin. So at this point, my hope is that we should be prepared when we come into the lab. We'll be able to see the results of our experiments. We'll be able to see the probability of the theory given the data. We'll be able to see the probability of it being a fair coin. We'll be able to see the probability of it being a two-headed coin. And So I look forward to seeing you there.